which of course tells you the amount of flow between every edge in order to get as much flow from S to T as possible. And our algorithm is, given a current flow, we're going to augment the flow to get a better flow. And the way we do that is we build this augmentation graph which says how much you can change the flow through every edge. And then...
Is this stuff on the test on Monday? Or
no.
This is the next one.
This will be on the exam.
Oh, okay.
Yeah, so next test on Monday is graph theory and loop invariance. And we're not going to, this won't be finished in time for it. And besides, I've made up the exam already and this isn't on it. So, but it's a fine topic. It won't be on test 4 because that's about greedy algorithms, or test 5, which is about dynamic programming. But it's a fine topic for an exam. All right, so the way we get a better flow is you find a path that a drop of water can travel from S to T, and then you push as much through there as possible. And we showed that if you push 2 through here, and then you push as much through you can here and as much as you can here, then you get a local maximum where you can't push any more forward. You can't simply increase the flow by increasing in every edge, but it's not optimal. And the reason is that we have too much flow through this edge. Somehow we have to decrease the flow in this edge while simultaneously increasing the flow from S to T. And the way we do that is, you can think about it as you standing on a sidewalk in which you can go 75 this way or 10 this way. Similarly, if you have 2 edges here, this says you currently have 0 flow because we're currently standing here, but you can flow, either push 75 this way or you can push 10 this way. Right? And so this is just what I'm saying there. You can go to the right that way or you can go to the left that way, corresponding to having flow of 10 this way or 75 that way. Now, if you currently have a flow of 15 this way, so you're currently standing here, then you can think, well, what happens if I walk 5 in this direction? Where am I going to be? Right? I'm clearly going to be at 20. Right? So here, if I push 5 more flow this way, then it increases the flow to 20. Everybody with me here? And how much can we walk this way if we're standing here? Well, it's 75 minus 15. We can walk 60 more in this direction. Right? Pretty straightforward. Now, the other direction... yeah, so this is kind of what I said. We can push it to 60 more this way. Right? So if we currently have a flow of F, and you're allowed a capacity of C, then how much more you can push that way is F minus C. Now the other direction is a little harder. If we're currently standing here and you walk 5 this direction, right, then you'll then be at 10. So what does that mean over here? Well, if we push 5 that way, then it's kind of like pushing 5 along this edge. But the problem is we have flow spiraling around. You have 15 going this way and 10 going this way. So they kind of cancel out to giving you only 10 going this way. Everybody kind of get that? It's pretty straightforward, though for some reason people do. All right, so if we walk 15 this way, right, that brings us down to 0. Similarly, if we push 15 flow this way, it's kind of undoing that flow of 15, bringing it down to a flow of 0. Right? Now, if we push 15 plus 5, and we push 20 this way, right, then that's going to bring us to negative 5. Right? Same in this direction. Do we want negative 5 flow in this direction? No, that's really 5 in that direction. So 25 is in fact the limit, right? If you walk 25, then it's going to get you to negative 10. So how much can you walk this way? Right? It's the 15 plus the 10 that you can walk this way. Right? So this is, if nothing else, for the exam you should memorize the following things. All right? So if you currently have a flow of F going this way, and you're allowed a flow of C in this direction, then the amount that you can change the flow in this direction is, first you can do F in this direction to undo this flow, and then you can do another C in this direction to give you a flow of C in this direction. So the amount you can change it in this direction is F plus C.
So even those are directed, they're not actually disjoint. They're like linked together. The amounts that they, like I'm thinking like say U to V was like one road, and then V to U would be another road.
Right.
You don't really look at it as one way and the other way. You actually have to compare the two of them together then.
Right. Sure, the difference. I mean, you can think about it as, so we want to assign a number here between 75 and minus 15. Right? And if it's minus, then it's going this way, and if it's positive, it's going this way. Or you can think about it as a highway going that way, one-way highway, and a one-way highway going this way, or whatever. People kind of getting this? Right, so this is just a summation of what we just said. You know, the capacity going from U to V is CUV, and from V to U is CVU. And we currently have a flow F from U to V. So what we build this augmentation graph. The amount we can go this way is this number minus this number. And the amount that can go this way is this number plus this number. Right? And if then you push W flow this way, then it's like walking W that way. So we increase the flow by W. Right? And if you push W this way, then it decreases the flow by W. Everybody kind of following this? Yeah? So certainly, if I wanted to give you a really easy question on the test, which I've done every year in the last million years, it would be, here's a graph of the current flow. Do 1-2 steps of this algorithm on it, right? And what would you have to do? You'd be given this graph, which tells you the capacity of every edge and the current flow of every edge, right? And then you would build an augmentation graph. Now this is the augmentation graph we built before, and it didn't allow me to do anything to this edge, right? Because it was at capacity. But that didn't work very well for us. So our new augmentation graph will say, look, we're allowed 2 in this direction, and we have 2 in this direction. So we can push 0 more forward, but we can push 2 in this direction, right? Similarly, this edge, we can push 1 forward, or we can push 19 backwards. People can see that? Right? This edge here, we got allowed 75 forward, so you can push 75 minus 50, which is 25. Right? Or this direction, we could do the 50, which undoes this, plus another 10 to give you 60. Right? Everybody, given this, can you figure out how to build this? It's pretty straightforward. All right, then given this, what do we do?
Take a new path.
We're looking for a path from S to T. Right? You do any bang, 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 look for a path from S to T. And let me give you a little hint. There could be many paths from S to T in theory, right? But when marking, it's nice if everybody gives the same answer, right? So if there was a unique path, it would make my life easier. So you can almost guess there'll be a unique path. So you look for any path from S to T, right? And now, instead of putting a drop along here, we want to push as much through there as we can. And how much can we push? Well, here we can push 1, here we can push 2, here we can push 1, here we can push 25. So the bottleneck, right, is here and here, which is 1, right? So we're allowed to push 1 more forward. and in the end, that's going to increase our flow from S to T by 1, right? Which in some ways is good, because you remember that our flow was 1 shy of being optimal, right? So we're going to augment this by pushing flow of 1. So then we build our new flow, right? We have here 19, we push 1 through, you're going to get 20, right? We have 2 here, we push 1 this way, what are we going to get? 1, right? It's 2 minus 1 is 1. We push, right, because we're going backwards. We go this way, we add on 1 to get 30, 51, right? So, oh, I guess we're supposed to do it here, right? So then, we add on, we subtract, we add on, and this is our new flow, right? And in fact, this is the example, the answer that we got when we did it the first time. Everybody remember this? All right, so now we do it again. We're given a flow. We build the augmentation graph, right? It's similar to what we did before. Here we got a flow of 1 and we're allowed a flow of 2. So how much are we allowed more forward is 1. How much more are we allowed backwards is 1. Right? People see that? That's why we have this 1, 1 here. Now we look, is there a path from S to T? And in this case, it's kind of a silly example because you can't leave S at all. Right? So there's no path from S to T, and so we stop. Everybody good with that?
Do you need to repeat that augmentation process in order to be sure that you've covered it?
Yes. Yeah, so the algorithm is you start with the 0 flow, and then you build an augmentation graph, find a path, add it to the flow. You keep repeating this until there's no path, and then you stop. Right? It's because it's kind of the hill climbing is you have a solution. You keep taking steps upwards until no local change will move you forward. And then you hope you're at the top. Well, you're certainly at the top of a local hill. You hope you're at the top of a global hill. So this is just a summary of what we did. Right? We did it the one time and we got this answer. And then we did it with our algorithm that didn't work and we got stuck. And then our new algorithm got us back to the same answer. All right, so here's the code. You're given a graph with weights, with capacities on their edges and the node S and T, and our loop invariant is we have a legal flow, and we build an augmentation graph. Remember, we have an edge forward. It's the C minus the F, or the C plus the F. This is the weights on the capacities. You find the path. You find the bottleneck in the path. Right? You add the flow to every edge in the path. And you come back up, you have a new flow, right? And when there's no path, when S is not connected to T in the augmentation graph, we jump out. All right, everybody got the algorithm? All right, so let's do an example here. Remember, we got the boys marrying the girls in a way so that the boys aren't allowed to marry the boys, and they can't marry lots of girls, and it's a shame, but that's the way the problem goes. All right, so we have here 3 matches, right? Maybe our current flow gives us 3 matches, but there is a solution with 4 matches, right? So you might say, how is this augmentation process going to get us from marrying 3 people to marrying 4 people? So here's a flow of 3, right? There's a flow of 1 here and a flow of 1 here and so forth. Everybody kind of see? Flow of 3. So we build the augmentation graph, and it's going to look like this. Why? Because we have a flow of 1 this way, but and there's a capacity of 1, so we're allowed to undo that flow. So this purple, what color is that? Kind of an orangey, means that we can undo the flow of 1, right? While here you can still have a flow of 1. Everybody can kind of see this augmentation graph?
The undo part, what's the...
Well, this is what I was saying, is if you have a flow this direction of 1, then it's kind of like we can push 1 this way. Even though you can't have flow this way, but that's what confuses people, is we're not allowed to have flow this direction because the arrow goes this direction. But we're allowed to change the flow in this direction by 1 because we currently have a flow in this direction of 1. So in the augmentation graph, this says we're allowed to change the flow by 1 in this direction. Right? We're allowed to change the flow 1 in this direction because we're adding 1 to a pipe that doesn't have any flow. Does that make sense? You got that? So this is our augmentation graph, and we look for a path in it. And one thing that makes it easy is that the path is unique. Right? I guess it comes down here. So there's the path. Right? And you see what happens is this guy, right? We're adding an edge here. This guy is getting married, right? Because we're adding flow here. But then this guy can't marry this person because this woman's already married, right? But she gets divorced, right? We push the flow backwards here. And then she marries him and she gets divorced. And he marries her and she gets divorced. And he marries her and they live happily ever after.
Isn't there like a flow that the girl's marrying the girl?
Where?
On the top going down to the bottom.
Here?
Yeah, so it goes down.
Right.
And then,
These are 2 boys.
okay.
And this woman here is currently marrying him and divorcing him.
And that guy's marrying that girl.
And he's marrying her, who's divorcing him, who's marrying her, who's divorcing him, who's marrying. It's a busy day. Right? Lots of flowers. Right? But you'll note we start by adding an edge and we end by adding an edge. It's an alternation of adding and removing, right? But we start with an adding and removing and end with an adding, so 1 more gets added than removed. Right? So in the end, we get an extra edge. And did we have an extra edge there? 1, 2, 3, 4. Yeah, that's 4. Well, this is only 3. Everybody kind of follow that? So that's what we did. All right, now we're back to our question. We have a new algorithm. We're taking a bigger step. Can we get stuck? Right? And we want to prove that no, you can't get stuck. And this is very hard to prove. We have to prove now that for any network, given any graph whatsoever that the world may throw at you, right? If you ran the algorithm, given any choice of augmentation paths, you choose this one, or you choose this one, or you choose this one, you're going to get a different. You're going to build up a flow. Given any flow as we go along, this algorithm is always going to stop with a maximum flow, with an optimum flow. Right? Everybody get what we're trying to prove? Now, this is a big statement, and right, that's what we're going to prove it. And it's not completely easy, but it's not so hard either. All right? All right. So this is my way of thinking about it. You won't see this in any book. I like to think about hill climbing, right? So there are 2 problems here. We have the one is the hill climbing problem, and we have the roof problem, right? So you're standing on Mars, right? And Mars has a hilly landscape, and your goal, of course, is to find the highest place on Mars to stand. But you can't breathe on Mars, so they built all these ceilings to hold the air in. And they built lots of exponential number of ceilings. We have another problem, which is to find the lowest ceiling. Right? So the primal problem, as I said, is there are an exponential number of places to stand, and our goal is to find the highest place to stand. And there's an exponential number. The dual problem is you have an exponential number of roofs, and your goal is to find the lowest roof. Everybody got what these 2 problems are? You like my little animations?
Yeah.
Not just a pretty face. All right, so we're going to prove there are various things that are going to have to be true. All right, the one thing that's true is every roof is above every place to stand. Right? Right? You take any place to stand and any roof, the roof is above the place to stand. Right? The roofs don't go through the earth, right? Or else they wouldn't be called roofs. All right, so the other thing, and so from that, we get for free that the minimum roof is above the maximum place to stand. Right? Everybody see how you get that for free? Now, one question is whether there's a gap here between, it's maybe the lowest place to stand, the highest place to stand is strictly below the lowest roof. And our goal is going to be to prove that actually, no, there's no gap whatsoever. They touch. All right? And what do you have to prove? We have to prove that for every place to stand, one of two things is possible. Right? Either you can tell me how to take a step so you find a better place to stand. Right? You can make progress. Or what?
Or you have the lowest ceiling?
Exactly. Or if you can't, the reason is because we can give a reason why you can't go higher. Right? Either you can go higher or I can give you a reason you can't go higher. And the reason you can't go higher is because there's a roof right at your feet. Right? No, is this picture right? No, because the roof can't go through the land. So what's actually happening is you must be standing there. Right? So we're saying here is for L's location, it says for every location that you could be, either there exists a new location that's higher than our previous location, right? Or there exists a roof whose height matches the height of where you're standing. People can read the first order logic? And, all right, what does this give to us? Is it possible, what is this here? This is a local maximum. Is it possible to have a local maximum? Well, if there was a local maximum and I was standing here, remember with these two things, right? It says, can I take a step to get to a higher place if I'm standing at a local maximum? Right? It doesn't say that there is a higher place, right? It says I can take a step to a higher place. Right? So from here, can I take a step to get to a higher place? Well, the step which defines the topology. Right? If I had bigger steps, then the topology would be different. Right? So the point of the picture is no, I can't step over there. Right? I have to go down first. Right? So from here, there's no one step which will take me higher, but neither can there be, right? Neither can there be a matching ceiling, right? Because that ceiling would have to, ceilings are flat, right? Ceilings don't curve around, right? Everybody get that? So that proves you can't have local maximums. You only have a global maximum, and also there's no gap. Right? So that's what we're trying to prove here, is that this algorithm network flows won't get stuck in a local maximum because there's no, there are no local maximums. We're going to get to a global maximum.
So can you explain again why you can't go down a little bit and go up? Why is that?
Well, in a hill climbing algorithm, every place to stand is a solution, right? But you're not allowed to, a hill climbing algorithm, the idea is that you only make local changes, right? So you say from this solution, we can make these little changes. And here the changes is an augmenting path, right? And so what this picture, this is a funny picture because a solution is this n-dimensional space, right? But the picture is supposed to indicate that it's a local maximum, that from here you can't make a small change that goes up. To get over here, you have to make lots of changes, go down and come back up again, right? And the goal of this is proving that there are no local maximums, because if you're standing here, then you can't take a step that goes up, right? You could leap to go up, but you can't take a step to go up, and neither is there a ceiling, right? All right, so this is proving that the primal and the dual have matching solutions, right? The highest roof, the height of the minimum roof is equal to the height of the maximum place to stand. Everybody kind of get what we're saying here? And this idea of having a primary problem and a dual problem comes up lots in computer science, well, at least with linear programming and various things. So it's certainly a useful concept. All right? All right, so I guess this is the proof that they're equal. Right? We proved that for every roof and every place to stand location, the roof's above the location. Right? We also proved this algorithm. So how do we prove this? Is, well, the algorithm keeps running, starting somewhere, it runs until eventually it gets a roof and a location that are equal. Right? Because if the algorithm says you can keep getting a better location, you keep getting a better location until it doesn't, and when it doesn't, it gives you this roof. So then we want to prove that these are equal. Right? How do we know that the roof, the minimum roof is below the roof for the algorithm? Less than or equal to? This is the minimum roof. So the minimum roof by definition is the smallest. So it's less than or equal to some roof that the algorithm happens to return. Right? And by our algorithm, that equals the height of the location that the algorithm returns. And the height of the location that the algorithm returns is definitely less than or equal to the maximum location, by definition of it being maximum. Right? People follow that? But we have the other direction. Why do we know that this is greater or equal to this? It's because we set that up here. Right? So we got the matching. Are people kind of following this? And the language that that people in theory uses is that the location, if I tell you a location here, right, it witnesses the fact that you can achieve a location that good. Right? It witnesses the fact that the height of the maximum is not smaller. You can actually get up there. Right? The location is a witness. And similarly, the roof is a witness. Right? The roof witnesses the fact that you can't go any higher. That there's no higher location. Right? If I tell you that there's a roof here, then you know that there's no place you can stand that's higher than this. Does that make sense? And this idea of witnesses come up a lot in theory. Right? So we have a witness that the answer is yes and a witness that the answer is no. And that's in fact kind of why we have a polytime algorithm for this. But we don't get into that until we get to NP completeness, which we might not get to at all. All right, so now let's go back to network flows and think about what our ceiling is. Right? Our place to stand, our primal problem, is to find the best flow from S to T. Right? So location tells you the flow on every edge. Right? But now we have to think, what is our ceiling? Anybody know what our ceiling is going to be? What's our proof that you can't get more flow?
The lowest number in that direction.
Yeah, one edge, is this a proof? What did we do? We drew some other thing on the board last class. Remember? All right, well, let's think about this example. What is the maximum flow in this? What's the maximum that you can go here?
1.
It's the 1. What's the maximum you can go here?
2.
It's 2. What's the maximum you can go here?
0.
0, right? So in some ways, it's a cut here, which tells us the maximum. All right, so this is kind of what we were saying before. That's what I was kind of saying, backwards. So this cut here, the maximum that can flow across this cut is 3, right? And somehow that witnesses the fact that you're never going to get more from S to T than 3, because you can't get more from this blob to this blob. Right? People see that?
You say you can't get more from U to B, from this side to this side?
All right, think about this as one blob and this is one blob. How much can we flow from here to here? You can flow 1 here, you can flow 2 here. You can't flow anything here because it's going the wrong direction.
Yeah.
Right? So the most that can flow from here to here is 3.
So that's the most recent joint.
Yeah, it's the border. Right? I'm going to talk about this as being Canada and this as being the U.S. Right? The amount that you can flow from Toronto to Berkeley is bounded by the border. All right? And what we're going to prove, so here we have the max flow is 3, here we have the min cut is 3, and we're going to prove that max flow equals min cut. Right? The maximum that you can flow here versus the minimum cut are equal. Right? Those are always equal. All right, so the primal problem is max flow. The dual problem is this min cut idea. Right? So we have to define the min cut problem. An input is a network exactly like we had before. Right? We have a graph with the edges are being capacities, and you have a node S and a T. And so here's an example of an input. Right? It's the same input that we had through the flow problem. Now, what's a solution? A solution partitions the nodes into 2 sets, U and V, such that S is in U and T is in V. And so here you can think of S being York and T being Berkeley. And I did my postdoc in Berkeley and I loved it there. You know, they're all a bunch of hippies down there. So, we want to flow from here to here. What are the various borders? Right? It could be, as I said, the Canadian-U.S. border limits the flow from Canada to Berkeley. Or it could be Ontario could be the border, right? Or Toronto could be the border, or York could be the border, right? Actually, what limits you to getting into Berkeley is likely emissions into Berkeley, right? Right? What does this do? I guess the UBC, right? Berkeley. That was the city versus the university. Right? Or you could have some really arbitrary cut. Right? And the value of a solution, given a solution, what's the value of the solution, is we call it the capacity of the cut. And that's how much can flow from the U side to the V side. So it's the sum of every node on the U side and every node on the V side of the capacity from the U side to the V side. Right? And so it's the sum of those guys going that way, and we don't do anything about the guys coming back. Right? We ignore the guys coming back because they're going in the wrong direction. People kind of got that? All right, so we're going to prove that max flow equals min cut. For every network, the maximum that you can flow through the network is equal to the min cut. Right? And how are we going to prove that? We have to prove that it's the same thing as the roofs and the place to stand. First, we have to prove for every flow and for every cut that the rate of the flow can exceed the cut. And it makes kind of sense that if you're having flow from Toronto to Berkeley, and you have a particular cut, like the U.S.-Canadian border, how much is flowing? Right? The flow can't exceed the capacity of the cut. Right? Intuitively, that makes sense. Right? And we also prove that for every flow, we have an algorithm that either finds a better flow or finds a cut that are equal. Right? Finds a witness for why your flow can't get better. Are people any questions about this? Or are you kind of following along? Right? And then the algorithm is going to, you start with, say, the zero flow, and you keep getting a better flow, a better flow, a better flow, a better flow, right? We use this thing here. It either gives us a better flow, or if it doesn't give us a better flow, it gives us a cut. So we keep getting a better flow until it can't give us a better flow, at which point it gives us a cut. Okay? And then when the algorithm stops, it gives us 2 things. It gives us a flow and it gives us a cut. Right? And the flow witnesses the fact that we can obtain this flow. Right? And the cut witnesses the fact that we can't get a better flow. Right? And that's how we know we have a better cut. So in the exam, many times I say, okay, I give you a flow. Okay, give me a better flow. Okay, here's a better flow. Okay, do another step. Oh, there's no better flow. I'll have a cut. Right? How do you know that you don't have a better flow? Right? Here's an exam question. Right? Everybody think about this. I give you a graph with the current flow. Right? Question 1. Give me do steps and finish this algorithm till it's done. What do? Given this flow, you build the augmentation graph, you find a path through it, you find the capacity, you augment the flow, you get a better flow. Right? Now you have a better flow. You build the augmentation graph, you look for a path through it, there's no path. Right? So then what should you do then? You should find this cut. Right? And then I say, how do you know that there's not a better flow?
No pause.
All right, we got no path, no path. How many people want to answer no path? How do you know that there's not a better flow?
Your current rate is equal to this capacity?
Yeah, right? So the fact that there's not another flow, that there's not a path, what does that prove? That proves, yeah, it's the right answer if you believe your algorithm works. But I don't necessarily believe that the algorithm works. Right? You come to your boss, you don't want to say, hey boss, I know this is the best answer because my algorithm gave it to me. Right? It's not very convincing. Right? How do you know that there's not a better flow? I have this cut. I have this cut that witnesses that there's not a better flow. The cut says I have a cut that matches the flow. So there can't be, and I know there can't be a flow better than the cut I have. Right? Does that make sense? This is a new technique of mine. As we go through, I tell you the questions that everybody got wrong answers to on previous exams. So if everybody's taking notes, you can all do well, assuming I give you the same exam. All right, so now we're going to prove those things that we said. We're going to prove that for every flow and every cut, no flow, the flow is less than the rate of flow is less or equal to the capacity of the cut. I mean, the intuition, as we said already, is, one thing that limits the flow from Toronto to Berkeley is the US-Canadian border, right? You just can't push more flow across than the border allows, right? And let's not spend too much time on this proof because it's pretty intuitive, right? The capacity of the cut is the sum of all edges going across, right? We can define another thing. We can define the rate of flow across a cut. Right? If I have a flow and I have a cut, then the rate of flow is the sum of the flows going this way, from this side to this side, minus whatever's coming back. Right? People kind of appreciate that? So the rate of flow across a cut, given a flow and given a cut, is the flow going across the cut minus what's coming back. And what's going to be true is that the rate of flow, given a flow, is going to be the same for every cut. Right? The flow that flows out of S is equal to the flow that flows across this border, which equals the flow that flows into to Berkeley. Right? And that can exceed the capacity of the cut. So how do we prove this? Well, it's just kind of from definition, right? This here is the stuff that goes, the flow that goes this way can't exceed their capacities, right? And we have zero coming back. And how do we prove this? We prove this by induction, right? We prove it by induction. We have no extra flow and extra leave. How do you start off with the cut around this, and you add one node, prove by induction. Right? We don't need to go into too many details of it. This level of detail, if you want, it's in the book, and I'm certainly never going to test you on it. People kind of get it by intuition now, right? Given any cut, the amount that flows this way minus the flow this way is going to be independent of where you put that cut. All right, here proof by induction, it's in the book. All right, so we proved that the flow is less than the capacity of the cut. All right, so now we want to prove that given any flow, we either get a better flow or we get a matching cut. Right, everybody remember that? So what's the algorithm? It's the algorithm we have already. We're given a flow. This is our current flow. We build an augmentation graph. We find a path through the augmentation graph. We augment, we find the bottleneck. We augment the path, right? Giving us a better flow. Everybody get that algorithm? Because almost guaranteed you're going to have to trace out a step of this algorithm on the exam. I mean, I'm going to, you know, at least I want you to, no, you shouldn't be able to pass this course unless you know how to do this. All right? So here's, now given we have another flow. So what do is, oops. I guess we're getting a new one. We got a new flow. We build a new augmentation graph, but there's no path, right? So our goal now is to come up with a cut, right? This is going to be our final flow. And what's our cut going to be? Is what we do is how do you, we have an augmentation graph here, right? Our goal is to find a flow, a path from S to T. What's the algorithm for finding a path from S to T? Is you start at S and you build up things that are reachable from S, right? In this case, it's a really dumb example because nothing's reachable from S. But you can imagine, hey, this is reachable. You know, you can get to U, and there's an edge from U to V, so you can get to V. But you build up what's reachable, right? So the set U is everybody who's reachable from S, and the V is everybody who's not reachable from S. Right? Does that make sense? In the augmentation graph. Now, how do we know that S is in U? It's because S is reachable from S. Right? How do we know that T is in V? Because it's not reachable. If it was reachable, we would have a path, in which case we'd be augmenting our graph. Right? Does that make sense? So this gives us a cut. Right? As I said, it's a bad example, but here have it. And now our proof, what we have to prove, is that the capacity of this cut is going to equal the rate of our current flow rate. Right? We're going to prove that. Right? So this is what we're going to prove. You know, our algorithm ran, and in the end, it gave us a flow, a final flow, and it gave us a cut. Right? And we want to prove that the rate of the flow is equal to the capacity of the cut. And how do we prove that? Right? We proved already that the rate of flow is equal to the flow across this cut, right? Because we proved that well, we sort of, you know, that induction proof. 5 minutes? All right, we can finish this. The flow across any cut are equal. Right, so we're going to prove that our flow across the given cut is equal to the capacity of the cut. And how do you do that? Well, here's our, you know, think about every pair of nodes UV. Right, we have a current flow. We currently have a flow this way, across the cut, and there's a capacity here. That's the capacity going this way, and there's a certain amount of capacity that can come back. Right. And then we want to prove that. So is contributing to the flow from across the cut? Is this guy is contributing to the flow across the cut, and this is contributing to the capacity. Right? That's right. What is the capacity across the cut? It's the sum of the capacities going this way, and we ignore the capacities going this way. Right? People good with that? Right? And what's the rate of flow is we add on any flow this way and we subtract any flow coming back. So to prove that these are equal, right, what do we need? We need that these are equal, that the flow any edge going this way is at capacity, and any edge coming back is at 0. Right? We need that these are equal and nothing here. And that kind of makes sense, right? If you have a cut here, we're at capacity across the cut Y. Any edge going this way is at capacity, and any edge coming back is, right, if you wanted to get as much flow from Toronto to Berkeley, you would have every border, the capacity going south, and nobody coming back, right? And then all those people go to Berkeley. Right? So now we have to prove that we have to prove that these are equal, and we have to prove that this is 0. Right? And how do we do that? Well, we built this augmentation graph, right? When we built the augmentation graph, what value did we put on this edge going this way?
0.
Well, we currently have a flow of F, but we're allowed a capacity, we're allowed C. So going this way is C minus F, right? And what do we have going this way? We could first undo this, and then we can do this one, right? So, right, it's this plus this, right? Does that make sense? People with me here? So, these guys are reachable from S, right? By definition, they're in U. These guys are not reachable from S, right?
Should the bottom arrow be the other way around?
Oh, sorry. Sorry. You're right that I've been saying it wrong. Here are two examples of edges, right? So this guy coming this way has a flow of, so we can augment it going this. I wanted the augment edges to go this way. So we want to show that these edges going this way are at capacity, and edges coming this way are 0. So these are two, this is U and U V, and this is U. These are different nodes. And if we have flow this way, then actually what we got it's this plus the capacity this way is actually what I meant. Right. So we have it. This guy here is how much can we push this way? It's this. We can undo this flow plus whatever capacity is going that way. So, and can we have edges going from here to here? Right, because these are not reachable and these are reachable. So if these were reachable and there was an edge here, then these would be reachable too, but they're not. Right? So that means we have no edges. So this has to be 0, which gives us that this equals this. Right? And these guys have to be 0, which tells us that this is 0. And that is our proof. And if you didn't quite follow all that, don't worry, because next class we'll give a quick summary of everything you need to know for the exam for network flows. It'll take about 5-10 minutes, and then we'll start on greedy algorithms. And then I think we'll almost be caught up again. Everybody good?
Question for the exam. Do you have any control over whether or not we can actually move the date?
Oh, you gotta be kidding.
No? Okay, never mind.
Yeah, that's the powers to be, right? The chances of little us moving the exam, it's pretty small. I suppose, yeah, certainly formally we could never do it, right? If we got 100% consensus and we found another room, we personally could not tell them, right? But my experience is the probability of you getting consensus from everybody in this room is pretty small.
Show of hands.
I mean, do you want it earlier or do you want it later?
Or earlier.
Earlier.
I don't even know when it...
It's 9 a.m.
Oh, you mean as in the morning?
Oh,
You don't care the day, you don't like the time.
Well, I would actually prefer to change the day.
Right.
So just have someone that's not doing those days, so either earlier or just not that week.